Hi everyone, in this segment we'll be looking at longitudinal waves. So what you have in front of you is a great example of a longitudinal wave. This is one of the examples we have on the website. You can click on one of the Java applets, just make sure you have Java installed. What you can see here is that we've got this wave energy. It's traveling from the top to the bottom of the screen. I'm following it here. So the energy is going downwards. But when you look at the actual particles, the particles here outlined in red are simply moving up and down, back and forth. So in this case, the motion of the particles parallels the motion of the wave energy. So that's why these are called longitudinal waves. Here's another great example on the PowerPoint you guys saw the other day. So you can see here the energy is going to the right, but the individual particles are simply moving back and forth. So again, the motion of the particles is parallel to the motion of the wave energy. You can also see here a great example of how the energy is transmitted through the wave without the particles actually moving. So when we look at this, there are going to be areas where you've got the particles very close together. Those are called compressions. You can see one over here, another one in this location here. And the areas in between where the particles are more spread apart, those are called rarefactions, not refractions, so be careful with grade 10. Now the wavelength's a little different here. Now the wavelength is measured from the center of a compression to the center of the subsequent compression, or the center of rarefaction to the center of the subsequent rarefaction. Measure from the center to side. That's the easiest spot to measure. So let's look at a couple of examples here. So what I have here is a simple example of a longitudinal wave. The lines represent the coils of a spring, for example, or it could be particles of air. Nonetheless, you can see here how the particles are closer together in some areas. So in some areas, you're going to have the compressions occurring. So these are my compressions. And in between the compressions, you're going to have your rarefactions, where the particles are more spread out. And remember, when you're indicating the wavelength, you measure from the center of a compression to the next compression center. This would be my wavelength here. Or I can measure from the rarefaction to the rarefaction center. I find it's much, much easier measuring from the compression to the compression. Let's look at an example here of drawing a longitudinal wave. So in this case, we're going to be drawing a wave that's longitudinal with a wavelength of 8 centimeters, or 8 boxes in this case. And we're going to draw 4 of these vibrations. So what I've already done is I've already put in some of the compressions. You can see here the compression. I started with the compression here. And I'm going to have another compression 8 centimeters away. Here's another one 8 centimeters away. Just like that, I put a couple of lines there. And in between, I put a few smaller lines. These represent the areas of the rarefaction. And you can quickly see how the energy would be transmitted this way, and the particles will be going back and forth. So what I have here, you've got compressions. Again, we're labeling. And we've got these rarefactions in between. And if you look at how many waves I drew, if you measure from the beginning, I've got 1 wavelength, 2 wavelengths, 3 wavelengths, 4 wavelengths. So 4 wavelengths all the way across that we drew. And that's it for this particular type of wave. So it's very easy to do. Just draw a couple of lines that represent, as I said, the particles, and show the compressions close together, the rarefactions separated. That's it.